Every time you send a message to a large language model, this pattern activates. Sine and cosine waves stacked at geometrically spaced frequencies encoding the position of every single word. Start with the number 1 on the complex plane. Now multiply by e to the IPI. That is a rotation of pi radians, 180 degrees. You land exactly on -1. E to the IPi plus 1 equals 0. The same 5-symbol equation is running inside the language model you use today and inside every quantum computer on Earth. Here is why it has to be. Let us look at this equation one symbol at a time. E, Euler's number, approximately 2.718, the base of the natural logarithm, discovered through compound interest. I, the imaginary unit, the number whose square is -1, introduced by Bombelli in 1572 to solve cubic equations. Pi, the ratio of a circle's circumference to its diameter. 1, the multiplicative identity, and 0, the additive identity. 5 constants from completely different areas of mathematics linked in a single equation. 3 operations appear: exponentiation, raising e to a power; multiplication, the implicit product of I and pi in the exponent; and addition. Each operation is used exactly once. Richard Feynman called Euler's formula the most remarkable formula in mathematics. Our jewel, he said. But this equation is not just beautiful. It is doing real work in the 2 most powerful technologies of our time. We will follow 2 pathways. One leads through the Fourier transform into the heart of modern AI. The other leads through unitary operators into quantum computing. And at the end, we will see why they must converge. We start with the Taylor series for e to the x. This infinite sum converges for every real number, and it also converges for every complex number. So let us substitute x equals I theta. Expanding, we get e to the I theta equals 1 plus I theta squared over 2 factorial, and so on. Now here is the key. The powers of I cycle with period 4. I to the 0 is 1. I to the 1 is I. I squared is -1. I cubed is -I. Then the pattern repeats. This means the even-powered terms are all real and the odd-powered terms are all imaginary. Look at the real part. 1 minus theta squared over 2 factorial plus theta to the 4th over 4 factorial minus and so on. This is exactly the Taylor series for cosine theta. And the imaginary part. Theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial. This is exactly the Taylor series for sine theta. Therefore, e to the I theta equals cosine theta plus I times sine theta. This is Euler's formula. Now set theta equal to pi. E to the I pi equals cosine pi plus I times sine pi. Cosine of pi is -1. Sine of pi is 0, so e to the I pi equals -1. Add 1 to both sides, and we have Euler's identity. E to the I pi plus 1 equals 0. Here is the complex plane. The horizontal axis is the real part. The vertical axis is the imaginary part. The point e to the I theta sits on the unit circle at angle theta from the positive real axis. As theta increases, the point rotates counterclockwise. Its real part traces out cosine theta, and its imaginary part traces out sine theta. One full rotation brings us back to where we started. Consider 2 points on the unit circle. Z1 at angle pi over 4. Z2 at angle pi over 3. Their product lands at the angle pi over 4 plus pi over 3. This is the fundamental rule. Multiplying complex exponentials adds their angles. Multiplication by e to the I theta is rotation by theta. There is another way to see this same rotation. In the language of matrices, multiplying by e to the I theta is the same as applying the 2x2 rotation matrix R of theta with cosine and sine entries. Same operation, different notation. And here is the key insight for what comes next. This matrix language generalizes to higher dimensions, to unitary matrices, to quantum mechanics. Pathway A begins with the Fourier transform. The idea is simple but profound. Any signal can be written as a sum of rotating phasors, e to the I omega t. The kernel of the Fourier transform is Euler's formula. Watch what happens with a square wave. 1 sine harmonic gives a rough approximation. 3 harmonics start to show the shape. 5 harmonics sharpen the corners. And with 15, the square wave emerges clearly. Each harmonic is a rotating circle in the complex plane, and their sum reconstructs the original signal. Now, where does this appear in modern AI? In every transformer model. The positional encoding from the original 2017 paper uses sine and cosine at geometrically spaced frequencies. Here is the encoding matrix. Each row is a position. Each column alternates between sine and cosine. Pull out any adjacent pair of columns. They trace a unit circle. This is Euler's formula applied directly. Each pair of dimensions is a rotating phasor. For a standard transformer with D model equals 512, there are 256 such circles running simultaneously for every single token. The same idea goes further. Rotary position embedding, or ROPE, used in Llama, Palm, and GPT-NeoX, literally rotates query and key vectors by position-dependent angles. The dot product then depends only on relative position. This is Euler's formula as architecture. Fourier features from Tanchik and colleagues in 2020 map input coordinates through cosine and sine before feeding them to a neural network. This single trick enabled neural radiance fields and the explosion of neural implicit representations. And the Fourier Neural Operator turns the entire Fourier transform into a trainable layer, learning to solve partial differential equations hundreds of times faster than classical solvers. From the Fourier transform to positional encoding, from Fourier features to neural operators, Euler's formula is the mathematical backbone of modern AI. Now let us follow the other pathway. Pathway B begins with a generalization. Euler's formula tells us that e to the I theta is a rotation of the complex number line, but we can replace the scalar theta with a Hermitian matrix H. The matrix exponential e to the IH is defined by the same Taylor series, with matrix powers instead of scalar powers. When H is Hermitian, meaning H equals its own conjugate transpose, the resulting matrix U is unitary. It preserves lengths. Scalar theta becomes Hermitian matrix H. Rotation in the complex line becomes rotation in complex n-dimensional space. And this is exactly what quantum mechanics uses. The Schrödinger equation says that the time evolution of a quantum state is governed by a Hermitian operator H, called the Hamiltonian. The solution is beautiful. The state at time t equals e to the negative IHT over h bar times the initial state. This is Euler's formula at its deepest. The factor of I is not decoration. It is what makes the evolution unitary, which means total probability is conserved. Strip out the I, and you get the heat equation. Probability would dissipate, not oscillate. With the I, the inner product of psi with itself stays equal to 1 for all time. A single qubit is a point on the Bloch sphere. Its state is parameterized by two angles, theta and phi, with Euler's formula appearing explicitly in the e to the I phi coefficient. Quantum gates are rotations of this sphere. Rx of theta rotates around the x-axis, Ry around y, Rz around z. Each one is a matrix exponential of a Pauli matrix, exactly Euler's formula generalized to 2 by 2 matrices. Look at Ry explicitly. Cosine and sine of theta over 2, the same rotation matrix we saw in section 3, now acting on quantum states. Every quantum gate is built from Euler's formula. In quantum machine learning, you chain together parameterized gates. Each gate has the form e to the negative I theta k times a fixed generator, gk. A classical optimizer tunes the angles theta to minimize a loss function. Here is the remarkable result. Schuld, Sweek, and Meyer proved in 2021 that the output of any such variational quantum circuit is a truncated Fourier series in the input data. The Fourier series, the same object from pathway A. An important note. Quantum machine learning is a mathematically beautiful and active research area, but it is not yet a deployed technology that outperforms classical AI on practical tasks. One more connection. In quantum mechanics, the position space and momentum space representations of a quantum state are related by the Fourier transform. The same Fourier transform from pathway A, Euler's formula, is the mathematical backbone of quantum mechanics, just as it is the backbone of AI. Let us put the two pathways side by side. On the left, classical AI, a signal reconstructed as a sum of complex exponentials, the Fourier basis. On the right, quantum machine learning, the output of a variational quantum circuit. Schuld, Sweek, and Meyer proved that this output is also a sum of complex exponentials, the same basis functions, the same mathematical structure. This is not a coincidence. Here is the deep reason. Whenever a process must preserve a quadratic quantity, whether it is the length of a signal, the energy of a system, or the total probability of a quantum state, and vary smoothly with a real parameter, the only way to do it is multiplication by e to the I theta, possibly with theta promoted to a matrix. Pathway A uses this because Fourier components have unit modulus, and the Plancherel theorem preserves the L2 norm. Pathway B uses this because quantum probability is the squared modulus of the state vector, and only unitary evolution preserves it. The convergence has three concrete bridges. First, the same fundamental object. The scalar e to the I theta and the matrix e to the IH are the same construction at different levels of generality. Second, the Fourier transform appears in both fields. Frequency analysis of signals and the position-momentum duality of quantum mechanics are the same operator. Third, and most remarkably, quantum circuits are Fourier models. Schuld, Sweek, and Meyer proved this in 2021. This convergence is not metaphorical, it is theorematic. E to the IPI plus 1 equals 0 is not a coincidence. It is the inevitable consequence of how rotation, preservation, and smoothness constrain mathematics. And that is why it appears at the heart of both artificial intelligence and quantum mechanics. From imaginary to indispensable. In 1572, Bombelli wrote down rules for the square root of -1 just to solve cubic equations. His contemporaries called these numbers imaginary, fictional, useless. Euler gave us the formula, Argand gave us the plane, Hamilton gave us quaternions, Schrödinger put I into the fundamental equation of quantum mechanics, Vaswani put sine and cosine into the transformer, Su put rotation into attention. A number once dismissed as imaginary now powers the two most transformative technologies of our century. Richard Feynman, in his 1964 lectures on physics, called Euler's formula the most remarkable formula in mathematics. "This is our jewel," he said. He was right, and we are still discovering new facets of that jewel today. Full references are in the description below. Thank you for watching.